Hello everyone, welcome to this lesson. So in this lesson, we're going to go through the Python code for the modified Newton-Raphson method, which is a method commonly used to find multiple roots. Now, if you remember, multiple roots are the roots where we have the function is tangential to the x-axis, as you can see with what we have here at 3. And this poses a few concerns. Now, we have 4 techniques that we have gone through: the bisection, false position, Newton-Raphson, and the secant. And because there's no change in sign around the 3, we mentioned that we can't use the bisection and the false position. And also, when it comes to the Newton-Raphson, despite the fact that we can actually apply it to multiple roots, the problem is the derivative at a multiple root, because it's tangential to the x-axis, is 0, which means as we get closer and closer to the xr, we get closer and closer to dividing by 0. So this poses a problem when dealing with the Newton-Raphson method. Now, the Newton-Raphson actually has a property when dealing with single roots. Newton-Raphson actually converges quadratically. As you can see here at the bottom, this is what a quadratic convergence would look like. And as opposed to the bisection and the false position, which actually converge linearly. But if we apply the Newton-Raphson to a multiple root, it loses its quadratic convergence property and actually converges linearly. So what we have done, we have created this technique, the modified Newton-Raphson, which protects us against dividing by 0 and also regains the conventional Newton-Raphson's quadratic convergence. And we have introduced the modified Newton-Raphson with this equation here. Xr is equal to xi. We have the function at xi multiplied by the derivative divided by the derivative squared minus the function at xi multiplied. And this is the big change here. We're dealing with the second derivative of the function. So if you're using the modified Newton-Raphson, you need the function, the first derivative, and the second derivative. So that being said, let's actually move on to the Python code. Now, the Python code is very, very simple code. Here we have, instead of defining the function and the derivative as we have done with the Newton-Raphson, we're also going to be defining the second derivative. Now, in this case, the function that we're dealing with is a cubic function. So it's x cubed minus 7x squared plus 15x minus 9. This gives us a derivative of 3x squared minus 14x plus 15, and of course a second derivative of 6x minus 14. Now here we have, since we're dealing with a multiple root of 3, the initial guess is 2.5. And also, if you've noticed, it's still a Newton-Raphson and it's still an open method, which means we are still dealing with one guess. And in this case, again, we're dealing with a guess of 2.5. Now, in terms of the main code that we have been dealing with thus far, the only change that is going to be done here is the definition of xr. Instead of defining xr in this conventional Newton-Raphson, we're going to be defining it in terms of this equation, as you can see here: xi minus the function xi multiplied dyxi divided by dyxi squared minus the function at xi multiplied by the second derivative at xi. And everything remains the same. Here we have initializing the a at 100. This is the application starts at 1. This is the header that I've explained before. And also, this is all the same. We get the et before we go to the next iteration, store the root for the next iteration, and also up the application, in this case, the modified Newton-Raphson. So let's actually run the code for, in this case, an initial guess for 2.5 and an approximate error of 0.1%. So let's actually do that. So if I run this, you can see that we have actually only gone through 4 applications of the modified Newton-Raphson, and we definitely got below 0.1% error, and this is an approximate error of 0.000079, and a true error of actually 0. And here, basically, we have found our multiple root at 3. So you can see here in just 4 different applications, we have converged very quickly into our root. And this kind of captures what I have meant earlier by quadratic convergence, which you can see here. In just 4 different iterations, as you can see here, it converged to here an answer very, very close to 0. So this is what a quadratic convergence looks like. So let's actually apply this apply the Newton-Raphson, the conventional Newton-Raphson, to find 3, because I actually want you to see how the conventional Newton-Raphson would actually converge to this answer compared to the modified. So I've included the Newton-Raphson here, and if you remember, it's here we have defined the f dy. Here I put the initial guess at 2.5. Let's actually change the error here to 0.1. So this is the same exact code that we have dealt with before. So the only thing that I have changed here is the function of defining its derivative and the initial guess. So actually let's run this code. So if I use the Newton-Raphson to find the multiple root at 3, it's going to take me 7 different iterations, and I have an error below 0.1% at 0.093831, and here 2.997196, so very, very close to the multiple root of 3. But I want you to notice something. Look at the approximate error. After 7 iterations of the Newton-Raphson, we are at 0.09. But of only 4 iterations of the modified, we're actually at 0.000079. So we're actually even below an error of 0.001. So you can see in just 4 different iterations, we didn't even reach, in 7 iterations of the Newton-Raphson, we didn't even reach the accuracy of only 4 of the modified Newton-Raphson. So this kind of captures what I've meant by quadratic convergence as opposed to linear convergence, as you can see here. Let me actually go through to see how many iterations actually is it going to take to go below 0.0001. So if I do that, so you can see if I'm going to use the Newton-Raphson to find the multiple root and get the similar accuracy as the modified, I'm going to have to go through 17 different iterations, and you can see 0.000091, and this one is 0.000079. So you can see even after 17 different iterations of the conventional, it didn't reach even the accuracy of the modified. So it is pretty impressive, and this shows you the power of a quadratically converging technique as opposed to a linearly converging technique. So there's one thing that I do want to mention. Now, when you are dealing with single roots, because the Newton-Raphson, the conventional Newton-Raphson, is quadratically convergent, that's why it's superior to the bracketing methods, because bracketing methods, the bisection of false position, are linearly converging. So when the Newton-Raphson comes in with its quadratic conversion, it's superior. But when it is applied to a multiple root, it loses that quadratic convergence and becomes linear. So that's why it makes the modified Newton-Raphson superior to the conventional Newton-Raphson. So kind of to recap briefly what you've learned in this lesson, we have introduced the Python code for the modified Newton-Raphson method in terms of the code. The only really difference is that now you're going to be defining the second derivative, and of course you're going to be defining the XR using the expression that we have here. Now with this lesson, concludes the series of roots of equations, and I hope you have seen how very, very simple techniques, as we have introduced here, can find very, very accurate roots to any equation you might be interested in, roots that are as good, if not identical, to the true value. If you can see here, as we have in just 4 different iterations, we have reached a multiple root without using any analytical means whatsoever. So that would be it for this lesson, and I will see you in the next series. Thank you very much.